In this section, we're going to talk about inference about two means from independent samples. So this is just hypothesis testing on two different means. So we can go straight into the 6 steps here. And of course, there's always conditions that need to be met before you start these 6 steps. And in this case, we have simple random sampling that needs to be done. These samples have to be independent from each other. That is important. We will deal with dependent samples. That'll be in the next section. And of course, these samples have to be from populations that were normally distributed. But if you didn't know that, then the sample sizes for each sample has to be at least greater than 30. And of course, each sample can't be more than 5% of the population size. All right, so let's go into the first steps. Step 1 is just like usual. It's your hypothesis statements. You're comparing two different means from different populations. So mu1 equals mu2. Of course, that's the same as saying mu1 minus mu2 equals 0. Right, if you just subtract that mu2 from both sides, that's what that is. What you're just saying is that there is no difference. The difference here is 0. Step 2, our significance level. That's usually given to you in the question. Our test stat here is going to be a t-test. And again, the test stat is always a difference between what we see from data. This comes from data here. And what we see in the null hypothesis, which would be mu1 minus mu2. And we just said that that's from the null hypothesis. And that actually comes out to be 0. And the degrees of freedom here is either the smallest of n1 minus 1 or n2 minus 1. Now, if you're going through the function in your calculator, you're not going to have to worry about that. To come up with the test stat and come up with the p-value, all we're going to do is use 2 sample t-tests in your TI calculator. Okay. Step 4, we're going to draw a picture. Step 5 is we're going to come up with our decision here based on p-value and your significance level. We're going to compare those. And then step 6, we're going to come up with our conclusion statement, which is essentially the same flowchart that we've been doing so far. Now, while we're at it, let's go ahead and talk about how to construct a confidence interval for the difference between two independent means. The true difference between two population means has some lower bound and some upper bound. Now, the lower bound would be your best point estimate, right? Which is x1 bar minus x2 bar minus the margin of error. And then the upper bound would be the same two terms, but in this case added. Now your calculator can actually come up with this interval. There is a function for that. It's 2 sample t interval. And of course, in both the hypothesis test and the test stat, you have 2 options. You can either put in data and you have lists, or if they actually give you summary statistics, then you just use the stats menu and you have to come up with sample mean, sample standard deviation, sample size for each one of the samples. And of course, you have to enter your confidence level. And I'm also going to show you how to actually come up with a confidence interval that's equivalent to the hypothesis test once we already go through those 6 steps. Okay, I'm going to show you how to do that in these problems because some of your homework questions may ask for that. All right, so example 1. Looks like we have data here, so let's go ahead and get our calculators ready to input this data. But let's go ahead and read this first. It says, a researcher wanted to know whether the state quarters had a weight that is more than traditional quarters. Okay. He randomly selected 18 state quarters and 16 traditional quarters. Weight each of them and obtain the following data. Test the claim that state quarters have a mean weight that is more than traditional quarters at a 5% level of significance. All right, so it looks like that's our claim statement right there. State quarters have a mean weight that is more than traditional quarters. You always want to identify the claim statement, which is right there in the highlighted sentence. All right, let's see if the conditions are met here. Do we have random samples? It looks like we do, yep. Are they independent from each other? Well, the fact that we chose state quarters and traditional quarters, there's no indication in the problem that they're dependent on each other, right? So I would definitely say that they're independent. Just a little bit of intuition can tell you that, right? Sample sizes are no more than 5% of the population size. Again, some intuition will also tell you that 18 quarters is not anywhere near 5% of all quarters that exist out there, right? Now, are samples large enough? Well, the requirement was that the population has to come from something that's either normally distributed And if you don't know that, then your samples, each sample has to be at least more than 30. Okay. Now in this case we have 18 and 16, so that means our population has to be coming from a normal distribution. Quarters are manufactured, and most things that are manufactured oftentimes follow some sort of normal distribution. Yeah, I'm going to assume that these are normally distributed. Now, we haven't actually gone through the exercises of doing a normal probability plot, and we won't in this class. That's something I decided to skip. But if you were to do something like that, it would reveal that it's a normal distribution. And that is something that's done in practice. But for our class, we won't deal with that. But I do want you to be aware that there is a method to test to see if something is normally distributed. And that's what that is. All right, so let's go ahead and go with step 1. We have our hypothesis statements. We are dealing with what? State quarters have a mean weight that is more than traditional quarters. So we're talking about a mean. The null hypothesis is always a statement of equality. And let's go ahead and identify what is considered 1 and 2. I'm going to go ahead and label state to be 1 and traditional to be 2. With that said, in the alternative hypothesis, what do we have here? Well, we have mu1, mu2. And what does this claim statement suggest? Well, that state quarters have a mean weight that is more than traditional quarters. So 1 is state, so this should be greater than, right? And that is our claim statement. Again, sometimes the claim statement could be the null hypothesis, sometimes it's the alternative. You have to be able to make that judgment for yourself, just based on the claim statement. And of course, it's important to identify which one's the claim in order to get the conclusion statement correct. Step 2, we have our significance level. Looks like it's 5%. Step 3, we're going to have to come up with our test stat. Now our test stat, it is a t-test, and just follow this formula here. Now, are any of those values given to us? Well, no, they give us data. Now, if they did give us all the stats here and did all the tedious work for us, then we can just calculate it. But in this case, we're going to put in the data. The thing about this is once we run this through our calculator and do what's called the 2-sample t-test, then it's going to output the t-value here, right, the test stat. And it's also going to give us x1 bar, s1, n1, x2 bar, s2, n2. And I'm going to go ahead and output all these values once we run it through our calculator. That way you can see that we all get the same values if you're trying this out on your own. All right, so let's go ahead and go over to the calculator and put this data in. All right, we're here on the calculator, the clear home screen. Go to stat. We're going to go to edit and go ahead and start inputting your data in here. We're going to put the state quarters in L1 and then traditional quarters in L2. Okay, so once you put your data in, again, make sure to double check all your inputs. Go through each data entry and check to see if it's correct. Okay, that'll save you a lot of headaches. All right, so let's go ahead and exit out of here. Go to stat. Let's go to test, and we're going to look for 2-sample t-test. 2-samp t-test. It's actually that 4th one right there. Okay. All right, we do have data, so make sure that's highlighted. And it'll say L1, L2. In my case, yeah, L1, L2. Keep the frequencies at 1. And the alternative statement here is that mu1 is greater than mu2, so make sure that that's highlighted. And then pooled, keep that at no. Now for pooled, what does that mean? Well, that just means if you actually happen to know that the standard deviation of both populations is the same, then what it can do, it just makes it an easier test to pass. Okay, we're always going to use a conservative approach and not assume anything. And so that means for us, we're going to say that pooled is no. Now in practice, if you are actually very confident that these populations have the same standard deviation, but you just don't happen to know what that is, but you know that they're the same, then that's when you would use pooled yes. But in this class, we're always going to use pooled no. Now let's go ahead and calculate. All right, so it gives us a bunch of outputs here. It gives us our test stat. In this case, it's 2.54 when rounded to 2 decimal places. It also gives us a p-value, which is 0.008. That's less than 1%, so that's definitely less than our alpha. So we're going to be able to reject the null hypothesis here. It also gives us a whole bunch of other outputs. It gives us degrees of freedom. And the degrees of freedom there are calculated in some bizarre way, which, again, for the purposes of this class, you don't really need to know what that is. But it does give you summary statistics for our two samples here. So the sample means for both samples. It also gives the sample standard deviations, and it tells us what our sample sizes were. So I'm going to go ahead and copy all those down. All right, these were the calculator outputs, and these are rounded numbers. All right, that's a complete step 3. And for step 4, we do have that output from the calculator, which is the p-value. And the shape of our graph is a bell shape because we're dealing with a test set that is a t distribution. There's a standardized t, so it's 0. It's at the center. And our test stat is 2.537. And well, that's to the right of 0. That's somewhere around here. Right? And what kind of tail test are we dealing with? Or is it a two-tail, left tail, right tail? In our case, it's a right tail. And how do we know that? Again, you always look at the alternative. It literally points in the direction of the way that we shade. Okay, so it's a right tail test here. So it's just a one-tailed right tail test. And what's the area of that shaded region? Well, we just calculated in the previous example. It's just the p-value. So that area is less than 1%. That's a complete step 4. So there's a lot that goes into step 4. Right, you have the correct shape of the graph, right? Because you have bell shapes, and you also have shapes like the chi-squared, which is skewed to the right, starting from 0. You have the correct number of tails that are being shaded. You have the 0 labeled, you have the test set labeled, and you also have the p-value, which is the area of the shaded region. So there's a lot that goes into that. Step 5, we have to make our decision, and the decision is made by comparing your p-value to your significance level. Our p-value being 0.0086. Significance level from step 2 was 0.05, and our p-value is less than our significance level. And again, what is it that we're actually saying here? Your p-value represents the probability of committing a type 1 error. And what is a type 1 error? That's when you reject the null hypothesis when the null hypothesis was actually true. And in our case, our p-value is 0.0086. So there's less than a 1% chance of us making an error if we reject the null hypothesis. And we're okay with that because we were willing to take it up to a 5% chance of making that mistake. So we're in good shape here. We're going to go ahead and reject the null hypothesis. We're willing to take that risk. Step 6, we're going to come up with our conclusion statement. Again, we're going to use that flowchart. So if we rejected the null hypothesis in step 5, and the alternative in step 1 was the claim, so we reject the null hypothesis, that means we have, in a way, we're accepting the alternative. We're accepting the claim statement, right? So we had enough evidence to support our claim, correct? And that's what the wording in that flowchart states. So let's go to that flowchart. All right, so back at this flowchart here, our claim was the alternative hypothesis. So we're going to go this direction. Did we reject the null hypothesis? Yeah, we did. So the wording starts off in this way. The sample data support the claim that, and then you just restate the claim statement. And for our claim statement, it was that state quarters have a mean weight that is greater than traditional quarters. Okay, so that's a complete hypothesis test there. Now, we're going to go ahead and construct a confidence interval that's appropriate for this hypothesis statement. As you notice here, we had a one-tail test, right? So we can actually convert that into a confidence interval here. So when we do have a one-tail test, the appropriate confidence interval for this is to make that one tail represent the significance level. Okay, so for in our case, our significance level was 5%. So that means when we come up with our confidence interval, each tail has to represent 5%. Okay, so that's a total of 10% in the tails. Therefore, the middle portion would be 90%. So let's go ahead and do that. You have a lower bound and an upper bound. So let's go ahead and go to the calculator here. Now, hopefully you did have your data still in your calculator at this point, and which I do. Let's go to stat, we're going to go to test, we're going to go to 2 sample t interval. So that's going to be down here somewhere. Looks like it's that one. All right, we do have our data still in our calculator under L1 and L2. Now in this case, our confidence interval that's appropriate for this hypothesis test, again, since it's a 5% level of significance, oftentimes people say, oh, then that means it's a 95% confidence interval. Well, that's not necessarily true. Okay, since this is a one-tail test, this 5% in one tail, that means there has to be 5% in the other tail. So that leaves us with 90%. Okay, so that's how you would do that. That would be an equivalent confidence interval for this hypothesis test. Again, we're going to do no for pooled. And let's go ahead and calculate. And there we go. 0.01736 and 0.08833 for our upper bound. Okay, so that's our lower bound and our upper bound. And what you'll notice here is that both of these are positive numbers, right? So let's draw a number line here. And we have our lower bound, which would be somewhere around here, which is 0.01736, upper bound being 0.08833. So we can say with confidence, with a 90% confidence, that the difference between mu1 and mu2 is somewhere between these two numbers here. Okay, where's 0 at? Well, 0 should be somewhere around here. Okay, so we're 90% confident that our true value is somewhere between these two values here. Our true difference between mu1 and mu2 are somewhere between these two values. And there's a 5% chance that's lower than our lower bound and higher than our upper bound. That's why we can say there's a significant difference between our mu1 and mu2, because 0 is not within that confidence interval. All right, let's go on to our second example here. Now, as you may realize here, we don't have data here, but hopefully they give us enough of the statistics for us to be able to do this. So let's read this. It says we have 2 independent samples. The first random sample of 40 items has a sample mean of 7.8 and a sample standard deviation of 3.3. The second random sample of 50 items has a sample mean of 11.6 and a sample standard deviation of 2.6. We believe that the mean of the second population is larger than the mean of the first population. Use alpha equals 0.10 to determine whether this is true. Assume distributions are normally distributed. All right, let's go down the conditions list first before we go into this. There is really no context to this problem. They're just saying this sample has a mean of such and standard deviation of such and such. We don't even know what they're measuring. It's just more of a bare bones example, okay, which is fine. It does make our conclusion statement a little easier to write. All right, so let's go down the conditions list. All right, do we have random samples? Do we have independent samples? Are sample sizes less than 5% of the population? And also, do we have either normal population or large samples? All right, do we have random samples? Well, yeah, I did say that we have random samples here. Independent samples, yep, 2 independent samples. Are the sample sizes less than 5% of the population? Well, it's kind of hard to tell because the context doesn't really tell us anything about what we're measuring here. But in this case, we're going to continue with the problem, even though we don't have enough information to make that determination. And then the last condition here is, do we have a normal population, or are the samples large enough? They do tell us that it's normally distributed, but even if they didn't tell us that last sentence there, the samples were large enough, 40 and 50. They were both greater than 30, so either way. All right, let's go ahead and get started here. Step 1. What is our hypothesis statements? We have mu1 equals mu2. And in this case, what was the claim statement? We always want to identify that first. Let's go ahead and highlight that. It says, we believe that the mean of the second population is larger than the mean of the first. The mean of the second population is larger than the mean of the first. All right, so if we write it like this, mu1, mu2, well, if the second one is greater than the first one, doesn't that mean that the first one is less than the second one? So you have to write the less than symbol there. And that is our claim statement. All right, that's a complete step 1. Step 2, significance level. They're saying it's a 10% significance level. Step 3, our test stat. It's going to be a t-test, 2-sample t-test. Here's the formula. Now, the one reason I do write these formulas is because it gives me an idea of what inputs I need. So we need x1 bar, s1, n1, x2 bar, s2, n2. And in our case, we're actually given all these values, right? If we go to the actual question here, for the first sample, we have the sample mean and the sample standard deviation. And the same thing for the second. So let's go ahead and copy those down. And of course, we can input all this into this formula here, get our own calculation here. But since we do need to find the p-value here, and the function in our calculator does both for us, might as well just use the function in our calculator to do this all for us. And that's 2-sample t-test. All right, so let's go to the calculator. All right, we're at a blank home screen here. Let's go to stat. Let's go to test. Look for 2-sample t-test. So that one. Now in this case, they actually do give us stats. We don't have data here. So we're going to go ahead and go over to stat, press enter on that. And you see how all the inputs change here. Now let's just go ahead and copy down what we have here. Okay, once you've put that all in, again, make sure that you inputted everything correctly. Always do a double check here. And the alternative here was that mu1 was less than mu2, so make sure that one's highlighted. That's the middle one here. Press enter on that. And then again, pulled is no. And let's go ahead and calculate. It gives us our test stat, which is negative 5.953. A p-value. It starts off with the whole number, 4.22615 times 10 to the negative 8, right? So anytime you see a whole number on your p-value, immediately look to the right, and you know it's going to be in scientific notation, right? Because p-values are probabilities. Probabilities cannot be more than 1, so there's no way that it can be a 4. So it is in scientific notation. Times 10 to the negative 8, that just means there's 7 zeros in front of that 4, so it's a very tiny number. And it also just outputs all our inputs that we put in. Sample means, sample standard deviations, and sample sizes. Our test stat is negative 5.59. All right, that's a complete step 3. Step 4, we're going to need the p-value from the output, and that is 4. Again, that is a very small number. If you really want the decimal equivalent to that, you would have to move this decimal to the left 8 times, right? Which will basically give us 7 zeros in front of the 4. All right, so that's the equivalent decimal form of this. So it's a very small chance of committing a type 1 error. I'm going to be very, very confident with rejecting the null hypothesis if that's my chance of being wrong. All right, so let's go ahead and draw the picture here. We have a t-test, so it's a bell shape. We have 0 at the center. Our test stat is negative 5.953, way out here. And we are shading in what direction? Well, the alternative tells us that we're shading in the left direction. So that is over here. And what's the area of that shaded region? Well, that's the p-value here. Okay, that's a complete step 4. Step 5, we're going to make a decision. Decision is made by comparing your p-value to your significance level. Significance level being in step 2, which is 10%. Our p-value was 4.226 times 10 to the negative 8, which is much less than 10%. And we're very confident in rejecting the null hypothesis because there's a very small chance of us being wrong in that decision. All right, let's go ahead and come up with our conclusion statement here. Since in step 5 we reject the null hypothesis, and in step 1 our alternative was the claim, then we reject the null hypothesis in favor for the alternative, correct? Which was our claim. So we do have evidence to support our claim. And of course, if you go through that flow chart, you can come up with that same wording. And here's the flow chart. Our alternative was the claim. We rejected the null hypothesis. So we can say that the sample data supports the claim that, and then we restate the original claim statement. And what was that claim statement? Well, this example was very abstract. It just said the mean of the second population is larger than the mean of the first population. Okay, again, to construct a confidence interval that's appropriate for this hypothesis, well, since this was a 10% significance level and it was a one-tailed test, we're going to do the same argument as before. In one tail, there's 10%. On the other tail, there's another 10%. Well, that's 20%. So what's left over? 80%. So 80% will be our confidence level. So let's go ahead and run this through our calculator. All right, if we go to stat and then test, and we go to 2-sample t interval, which is that one. In our case, we do have stats, and these inputs should be the same as before if you haven't changed anything. The only thing we have to adjust here is the confidence level. In this case, an appropriate confidence level would be 80%, 10% in each tail. And let's go ahead and say pulled no and calculate. All right, our lower bound is negative 4.626 and our upper bound is negative 2.974. Now, before I do go on here, if for some reason you have to express these answers with more decimal places than we have here, then just note that these values are stored in your calculator with more decimal places. The way to actually access the lower bound and the upper bound is through the menu bars. Okay, let me actually just show you that in case you run into this issue that you have to input this value into, let's say, like a online homework. Okay, so we can go ahead and quit out of here. If you go to vars, which is right there, and you go down to statistics, and what you'll see here is a whole list of variables, and these are all just stored values from what you just last calculated. Okay, so for us, if we go up to test, under test, these are all test stats, like the last test stats that you calculated, like that p is the last p value that you calculated, the z, the last z value that you calculated, and so forth. So if you go all the way down, you will actually get down to where it says lower. Okay, that's your lower bound, and you also have one that says upper. If you just press enter on that, it'll bring you back to the home screen. And if you press enter again, you see how it gives you a lot more decimal places that you weren't given in the output in the previous menu. So this is how you get more decimal values if you needed it. All right, so we have negative 4.626, upper 2.974. Now it's our confidence interval. Again, if you look at the number line here, we have our lower bound and our upper bound. This is a negative 4.626, and this is a negative 2.974. Where would 0 be? Well, 0 would be like way out here. And this represents an 80% confidence interval. There is a 10% chance that it's to the left of our lower bound. And there is a 10% chance that it's to the right of our lower bound. And the fact that 0 is not in our interval means that we are going to reject the null hypothesis because the difference between our mu1 and mu2 is significantly different than 0. Okay, that's it for this section. Thanks for watching.